Good morning. Today we're going to look at the derivative of the exponential function e to the x, as well as its more generalized version a to the x. So first off, what the heck is e? E is just a number. It's just a number. So it's a number like pi is a number or 7 is a number. It's more similar to pi in the sense that it is irrational. The decimal values never repeat. They go on forever and ever and ever. So how do we formally define this number e? I mean, I'm sure you've seen it in a previous class, maybe in another math class or science class, or maybe even a business class in the context of continuous interest. Well, e is defined as the limit as n goes to infinity of 1 plus 1 over n to the nth power. So I'm sure you haven't seen the definition like this before because you haven't been exposed to limits before this class. But my guess is that if you saw E in a pre-calc class, hopefully your instructor said, oh, E is what this quantity gets closer and closer to as n gets larger and larger. So instead of using the limit terminology, they probably said, oh, as this thing gets larger, as the n value gets larger and larger, which again, we now know as a limit. So I'd like you to pause the video for a second and use your calculator to actually plug in larger and larger values for this. Well, if you do that, hopefully you did, you'll see that E is approximately 2.71828. Now, again, this goes on forever and ever, and we have to be aware of that because a lot of times, especially in a science class, you say, oh, E is 2.71828. That's not entirely accurate, just like pi is not 3.1415. The decimals go on forever and ever. But it's approximately this. Okay, so that's what E is. That's how it's defined. There's actually another equivalent definition of E, and we're going to be using that today. What I'm going to do is I'm going to let H be equal to 1 over n, and I'm going to rewrite this expression in terms of H's. So let's think about this. If n is going to infinity, what is h going to? Well, hopefully you said if n is getting larger and larger, then 1 over n is getting smaller and smaller, so that h is getting closer and closer to 0. So this is 1 plus h. This n, well, let's see, h is 1 over n, but if that's true, then n times h is 1, and if that's true, then I guess n is 1 over h. Okay, so we could write it like this. So again, I invite you to pause the video, plug in numbers that are getting closer and closer to 0. Technically, this actually should be from the right side because n is approaching infinity, so these guys are positive numbers. Plug in values that are getting closer and closer to 0 into this guy, and once again, you should get something that's getting closer and closer to 2.71828. All right, so that's what E is. What I want to study, though, is I want to study the function e to the x. So I'm fully aware that we can use our calculator to graph anything, or just go online to graph anything you'd like. But there are definitely some basic functions that just pop up all the time. You want to have these guys committed to memory, and you're going to memorize this thing by understanding it. So e to the x is one of them. So let's look at this graph. Well, e to the 0 is 1. Why is that? Because e is just a number. It's about 2.71828. And you take any number that's non-zero, raise it to the 0 power, and you get 1 back. So it's going to cross through 0, 1. As we plug in larger and larger x values, again, this is just a number. So number to larger and larger values gets larger and larger. So e cubed, e to the 4th, e to the 5th. So this thing is exploding up this way. As I put in smaller and smaller numbers, such as e to the -1, e to the -2, etc., what these negative exponents are doing are they are flipping this guy. So this is just 1 over e to the first, 1 over e squared, etc., etc. So as I go out this way, my e to the powers are getting smaller and smaller because they're just 1 overs. Finally, I think a lot of people are a little bit lazy about drawing the asymptote, but we do have to realize that this function will never cross 0 because 1 over, I don't care what this number is down here, is never going to equal 0. So this is the graph of e to the x. So what I'd like to do is come up with the derivative of e to the x. Well, I'll give you a second, pause the video, see if you can come up with the limit definition of e to the x. All right, hopefully you gave that a shot and you said, oh, that's just e to the x plus h minus e to the x all over h. F of x plus h minus f of x over h. Pause the video again. Let's see if you can simplify the top using properties of exponents. Well, hopefully you said e to the x plus h is e to the x times e to the h. It's an exponent property. So that we can then pull out e to the x. So we have the limit as h goes to 0, e to the x times e to the h minus 1 all over h. And we've talked about this before. When you have something in the numerator, you can actually put it right here. And if I put it right here, this guy is with respect to x. The limit is with respect to h. So the e to the x is constant with respect to h, so we can pull it outside. So this becomes e to the x times the limit as h goes to 0, e to the h minus 1 over h. So that's the limit that I want to study. Well, if h is small, so for small h, we know that e is approximately 1 plus h to the 1 over h. So pause the video and see if you can explain to yourself why that's true. Well, hopefully you said that e is the limit as h approaches 0. So if h is close to 0, it's going to be approximately this value. So that's where that's coming from. Well, if this is true, then I can raise both sides to the h to get that e to the h is approximately 1 plus h. So 1 plus h times h is just 1. So e to the h is approximately 1 plus h for small h. So as a little parlor trick that you can do for your friends, I'm not sure that any of your friends would be interested in this, but you could say, hey, I can compute e to the h in my head for small h's. If h is 0.001, I know for a fact that e to the h is approximately 1.001. You can check it out. Plug 0.001 into your calculator, you'll get approximately 1.001. All right, so maybe win a bet that you can compute that faster than somebody using a calculator. Anyway, if e to the h is approximately 1 plus h, then e to the h minus 1 is approximately h. Okay, so we know that this is true if h is small, and I want to compute this limit. As I'm erasing this side of the board, see if you can then figure out what the limit as h goes to 0 of e to the h minus 1 over h is. Well, if this is approximately this, again, this is for small h, then I guess e to the h minus 1 over h is approximately 1. Therefore, as h approaches 0, this guy is going to be 1. Therefore, if f of x equals e to the x, f prime of x equals e to the x. It couldn't get better. As long as you know that you're working with e to the x, the derivative is e to the x. So as an example, what's the equation of the tangent line to e to the x at x equals equals 0. Let's give this a shot. Or, even better, pause the video, see if you can give that a shot. You have all the tools, see if you can figure that out. Right, hopefully you pause the video, you said, oh, f prime of x is e to the x. So f prime of 0 is just 1. That's just e to the 0. So that's my slope. So we have y equals 1x plus b. Let me just draw a picture so we can see this. Line that we're interested in, I want this guy. Well, this line goes through the point 0, comma 1, by what we talked about earlier. So 1 is equal to 1 times 0 plus b. So I guess my b is 1. So I guess that line is just y equals x plus 1. Right, so that's the derivative of e to the x. In general, we could talk about the derivative of a to the x. So now a is any non-zero constant. This general formula is something that we're not going to prove today. We will prove it when we get some additional tools. So I'm just going to tell you today that the derivative of a to the x is a to the x times the natural log of a. So as an example, the derivative of 3 to the x is 3 to the x times the natural log of 3. In fact, we can use this formula for e to the x. Again, it's more general. Let's see how that would work. Well, by this formula, again, we'll prove this in a future lecture, is e to the x times the natural log of e. Well, what's the natural log of e? The natural log of e is just 1. So this is e to the x times 1, or what we suspected, e to the x. All right, that's the derivative of the exponential function, e to the x. It's my favorite one because I don't have to remember anything. The derivative of e to the x is e to the x. Then we have this more general formula. The derivative of a to the x is a to the x times ln of a. Thanks for listening, and I will see you next time.